Hey guys, Mrs. Dans here. So today we're on lesson 9 and we will be evaluating functions given a function rule, which means that we will have to work with function notation. It's something that we will continue to practice all year long. And just a reminder that a function means that each input has one and only one output. You could start the do now on your own, but I am going to go over it right now in the video. As for your lesson 8 homework answers, they are posted in your Google Classroom and you should be checking that on your own and be ready to ask me any questions when you see me next. So we have to define the following. Counting numbers, remember those are the numbers that we say when we count. So when we first learned how to count, we start with 1, 1, 2, 3, and so on. So I'm going to write that in set notation. So we use the squiggly brackets. And this shows that it doesn't include any decimals or fractions because you follow the pattern. And it's showing that it goes on forever. Whole numbers are very much like counting numbers, except this is when we introduce the number 0, right? When we count, we don't ever say 0 because we're always counting objects that are there in front of us. But the number 0 does exist. It is a number. If I had 3 apples and I took away 3 apples, I have 0 apples. So they decided to call those whole numbers. So the whole numbers are the counting numbers with 0 included. So the only difference between counting numbers and whole numbers is that number 0. Integers are where we introduce our negative numbers. Now it's not all negative numbers because integers are the whole numbers and their opposites. So no negative decimals or negative fractions, just negative whole numbers. I can write this in set notation by starting with ... because now it's going forever in both the positive direction and the negative direction. Remember when we were doing our interval notation, when we were doing inequalities, we would say like it approaches negative infinity or positive infinity. So right now this is going off to negative infinity. I would have a -3, -2, -1, 0, 1, 2, 3, and it's going to approach positive infinity. So this is how we can write integers in set notation. Rational numbers, we can't really write it in set notation because there are just so many rational numbers. Rational numbers are numbers that can be written in the form of A over B. Can be written in the form A over B, where A and B are integers. So a lot of people say, oh, you mean our fractions? Yeah, I do mean our fractions. I just don't want a decimal in our fractions. That's why we say where A and B are integers. And there's actually something else I'm going to say. So A and B are integers and B does not equal 0. Why doesn't B equal 0? Remember my shirt, right? It's all fun and games until someone divides by 0. We can't divide by 0. That would be undefined. So therefore, it's not a rational number. Irrational numbers are, I guess, kind of like the opposite of rational numbers. If rational numbers can be written in a form of A over B, that means irrational numbers cannot be written in that form. Things that can't be written in the form of A over B, there's a famous one. It's the number pi, right? Pi, sometimes we see it in its decimal form, and it's like a rounded decimal form. Some people say pi is 3.14. That's an incorrect statement. pi is approximately 3.14. The digits in pi actually go on forever. So if we were to talk about decimal forms of numbers, so I'm going back to our rational numbers again actually. If a number can be written as a fraction, it can be written as a decimal. The decimal form of a rational number is either a terminating decimal or a repeating decimal. So I'm going to say it includes terminating and repeating decimals. Some people are shocked that repeating decimals are here. I'm just going to give you some examples. Definitely 1 over 2 is written in the form of a over b, right? And this decimal form of this fraction you all know to be 0.5. 1/3 obviously is written in the form of a over b, and this decimal form is 0.3 repeating, right? The 3 continues forever. The thing about irrational numbers is that it's not terminating and not repeating. It's like a crazy decimal that goes on forever and never repeats. It's pretty crazy, right? That's pretty irrational. Irrational in our English language means kind of acting strangely. It's pretty strange that a decimal number would go on forever and never repeat. So I'm going to say that the decimal form of irrational numbers are non-repeating, non-terminating, decimals. And a famous one is pi. There are plenty of others, and we'll talk about that as the year goes on. Our real numbers consist of both rational and irrational. So the real numbers are the rational and irrational numbers together. So that's like every number that you know about. There are, believe it or not, some numbers that are called imaginary numbers. And we could talk about that as the year goes on also. Right now, pretty much any number you've been exposed to is a real number. And then those real numbers can be classified down into smaller categories, which are counting numbers, or whole numbers, integers, rational, and irrational. Anyway, we talked about functions yesterday. A function lots of times has a rule attached to it, and it means that if you're given an input, you can then figure out what the output is. Because remember, for a function, each input only has one output. These inputs and outputs can be seen in equations, graphs, tables, and even in words. So let's do example 1 here. Consider the function rule. Multiply the input by 2 and then subtract 1 to get the output. My brain actually thinks as an equation first, so I'm actually jumping down to part B. It says write the equation. So I'm thinking about multiplying the input by 2, and we like to use the variable x to represent the input. So multiply the input by 2 and then subtract 1 to get our output. Now we can use y as our output, but when we're talking about function notation, we actually like to use that thing called f of x. This is, I always say, it's like a fancy way of writing y. F of x is y dressed up all fancy. It's kind of like, you know, when I go to a wedding, I'm still me, but, you know, I've got some nice fancy clothes on compared to, you know, when I am, you know, coming to teach. So I'm still the same person, I'm just dressed up fancy. So f of x is really y. How come they decided to use this notation for functions? Well, you'll see that it's really nice that each function can get their own name. This f is the name of the function. We actually don't have to always call it f. We can call it g or h or j. We can really call it anything. F of x is like one of the go-tos, one of the ones that we use most often. But if I'm talking about two functions at the same time, I'll call one of them f and the other one g. So why is there this x in parentheses here? That's what confuses people. It doesn't mean multiply f times x. It doesn't mean that at all. It's telling us that x is our input number and f is the name of the function. So it's saying let's use x as our input and the function's name is f. So if we go back up to our table, here's our inputs. You can see that they called them x, and we want our output that they're calling f of x. So here's a nice thing that they could say. If our input is 0, sometimes they like to say, okay, I'm going to use function f. I'm going to input a 0 into the equation. So remember, we said that our equation is f of x equals 2x minus 1. So I'm asking you what f of 0 is. Instead of just putting like a 0 in this column here, I could say just this, and it means use function f, plug in a 0, please. So I say, okay, I'm going to use function f, which says 2 times the input minus 1. 2 times 0 is 0. 0 minus 1 is negative 1. So f of x is equal to negative 1. So what I could say is when I evaluate f of 0, my answer is negative 1. We are going to get used to this notation. Please no panicking just yet. Keep calm. We can do this. This is just a new notation that actually kind of saves us some writing, right? Us mathematicians, we're coming up with symbols for everything. And we really prefer not to write words. We make shorthand ways of writing these things. So when I want to evaluate this function, when x is 1, I could ask you, what's f of 1? That's my question. What's f of 1? I'm really saying, can you please plug in a 1 in place of x and tell me what the value is? Oh, okay, I'll do that. So 2 times the input minus 1. 2 minus 1 is 1. Therefore, f of 1 equals 1. This is a sentence. It's saying when I plug in 1 for x, my output is 1. How about the next one? I'm asking you, what is f of 2? What does f of 2 equal? Oh, let me plug in a 2 in place of my input. 2 times 2 minus 1. 4 minus 1 is 3. What is that 3? Oh, that's the value of f of 2. So you notice the words that I've been using too, right? This f parenthesis 2, I've been saying f of 2, the word of, O-F. F of 2 equals 3. Finally, they're asking me, what's f of 3 equal to? What do I get when I plug in a 3 in place of the x? Well, let's see. 6 minus 1 is 5. Oh, f of 3 is equal to 5. Okay, so we're already starting to use this function notation. We took the words, wrote it as a function, then we were able to do our table of values. A table of values really is a bunch of points to plot, right? If my input was 0 and my output was negative 1, I can plot that point. If my input was 1 and my output was 1, I can plot that. My input is 2, my output is 3, and my input is 3 and my output is 5. Let's go plot those points. I'm going to say I'm going to use a scale of 1 on both the x-axis and the y-axis. If you're using a scale of 1, you don't really have to label it. You can if you want to, though. So the point 0, negative 1 is here. The point 1, 1 is here. The point 2, 3, and the point 3, 5. Look at that. They land in a straight line. And that's because, really, it's a linear equation. This is a linear function. I can connect this with points, with lines, I'm sorry, and put arrows at the ends. and I could just call this f of x. I don't have to write the name of the equation on the entire line. I can just call it f of x. So that's a good reason for maybe, using a function name. It's less writing. I don't know. Are us mathematicians lazy? I don't like to think I'm lazy. I could just do things kind of quickly because I know all the symbols. So in the function rule from part B, what input would be needed to produce an output of 17? Do you hear those words? What input would be needed to produce an output of 17? They want to know f of what number equals 17. In my table, I'm going to get a 17 as an answer. I want to know what did I put right here in place of x to get 17. So it's an equation we have to solve. So this is how come it's important to be able to solve equations. I could add 1 to both sides. 2x equals 18. I could divide both sides by 2. So x equals 9. Oh, I need an input of 9. The input of 9 produces an output of 17. So you have to be careful of your input-output, right? Up here, I'll come back up here because I want you to learn this function notation. When I ask you what does f of 1 equal, I'm giving you the input. The input is given. You have to find the output. But when I write it this way, you have to find the input that gives you this output. Find the input for this output. Okay? So let's move on. I might jump around a little bit. I might not do every single question in this lesson. And you know that's how I teach anyway. So what I want to do is actually jump to example 3 because I just want to make sure I use my time wisely. Example 3 is a pretty important one because it's using this function notation where they give us the inputs and we have to find the outputs. So I definitely want to do 3, and I'll probably go back to 2. But 2 is a little more straightforward. I think 2 you'll understand pretty easily. This is the one that kind of is way brand new to you. So the squaring function, they decided to call this the squaring function. Let's take a look at this function that's named f. Why is it called the squaring function? Oh, do you see they're squaring the input, right? So our input is represented by the variable x. The name of my function is f. And if they give me an input, I'll be able to find the output. And you know what? If they give me the output, I should be able to go in reverse and find the input. But it looks like in all of these problems, they're giving me the input, right? This is a question, believe it or not. It says find the value of the function when x is 0. That's what it's telling you to do. Find the value of the function when x is 0. So it means plug in a 0 in place of x. I'll plug in a 0 in place of x. And what is 0 squared? What is 0 times 0? You're right, it's 0. So f of 0 happens to also equal 0. Not always true that the input and output are the same. Like if we take a look at this one, they want me to plug in a 3 in place of x. So they're asking us what 3 squared is. What is 3 times 3? You're right, it's 9. So f of 3 is equal to 9. When I plug in a 3, I get out a 9. Can be written as the point 3 comma 9. My input is 3 and my output is 9. On this next one, they want me to plug in a -2. You need to get used to maybe always plugging numbers in parentheses. If I went back to this first one, I could put parentheses around the 0. 0 squared is 0. I could put parentheses around the 3. 3 squared is 9. I need parentheses around this -2 because they're asking me to do -2 times -2. So the parentheses are actually necessary. So f of -2 actually turns out to be a +4, right? Because negative times negative is positive. You didn't really learn square roots yet, so we're gonna like skip this for now. The next one, f of 2/3. So when I plug a 2/3 in place of x and square it, they're asking me what's 2/3 times 2/3. So f of 2/3 turns out to be 4/9. And now I like this question and this question because it goes back to our polynomial unit. What are they asking us to do? They're asking us to plug a in place of x. That's what they're asking me to do. So they gave me the function rule up here. This is called a function rule. The function rule says f of x equals x squared. And what it's telling you is whatever your input is, you're going to put it right there in place of the x. So my input is a. Let's put it in place of the x. I'm done. There's nothing else I can do here, right? I can't evaluate a squared. I don't know what a is. So f of a is equal to a squared. This one's even way more important. This whole expression here is my input. That expression has to be put in place of x. So in place of x, which is going to be squared, I'm putting in a plus 3. Ooh, look at this. A binomial squared. Doesn't this really mean a plus 3 times a plus 3? And don't you dare tell me it equals a squared plus 9. Not true, not true, not true. Don't forget we have all of this distributing to do. Or some of you like doing the box method. It turns out to be a squared plus 3a plus 3a plus 9. Let's simplify it. I'm coming over here because I ran out of room. I get a squared plus 6a plus 9. There we go. So part B is a pretty interesting question. What subset of the real numbers could be used as the domain of the squaring function to create a range with the same output values as the sequence of square numbers? So you have to like read those words and really understand what it's asking. So what real numbers could be used as the domain? Remember we talked yesterday that a fancy word for input is domain. So they're asking what could you use as the input in order to get this output. So what number would I plug in to get out a 1? What number would I plug in to get out a 4? What number do I plug in to get out a 9? What number do I plug in to get out a 16? What number do I plug in to get out a 5? So remember, this was our squaring function where we take the input and square it. So what number squared is 1? It's a 1. What number squared is 4? That would be 2. What number squared is 9? That would be 3. What number squared is 16? That would be 4. What number squared is 25? That would be 5. So this is like our inputs right here, while this is our outputs. So what are these numbers? Think back to your do now. Yeah, those are the counting numbers. And that's what they were asking. What subset of the real numbers could be used? Oh, we could use the counting numbers to get those outputs. So they gave us the outputs and we were looking for the inputs. Let's just quickly look at this question that I skipped. This, I think you can answer the question without me. I just want to make sure you're good on your homework. So look, they give us a few different functions. So this function is called f, this function is called g, this function is called h, and this function is called j. So for your homework, you're going to look at the correct function. Here they say use function f, and that's my input. So plug that in place of x to figure out what your output is. If I do 6 times 0 minus 3, 0 minus 3, I get -3 for my answer, right? And there's all different functions for you to look at. I'm just going to skip around. If I did this one, now I have to look at function h. And they want me to plug in a -1 for my input. So I guess h says negative, and then in place of x, I put my input. So -1 is a +1. And then you can see that some of these are asking you to do two things. Like I have to find out what g of 2 is, get an answer. Find out g of 1, get an answer. Whatever those two answers are, add it together, and that will be my final answer. On something like 8, I guess we'll do 8 together. You always do what's inside the parentheses first, so they actually want me to do f of 0 first and get an answer. So I want to look at function f, and I want to plug in a 0. So function f says I have to do 6 times the input and then subtract 3. 0 take away 3 is -3. But this is in parentheses with a g here. Oh, now they want me to find g of -3. So now I'm going to look at function g, and function g says I'm supposed to do 0.5 times 4 to the x power, and x in this case is a -3. Now you'd be able to do this on your calculator if you wanted, but I'm hoping you remember your negative exponents. I'm going to change that 0.5, believe it or not, to a fraction. I like fractions better, especially because when I do 4 to the -3rd, remember that means 1 over 4 to the 3rd power. This is back to unit 1. So I want to do 1/2 times 1 over. 4 times 4 is 16. 16 times 4 is 60, right? Yeah. So I get 1 over 120 as my answer for 8. So I'm going to say you go for this, do up to number 22, and I'll answer any questions when I see you, but you are not allowed to say I can't do this. Okay, you're going to plug whatever this number is in for x into the function they're talking about. You can do it. These are the polynomial ones that we even did something like it in the lesson. So I'll talk to you soon. Have a good day. See ya. Bye.